Well, good afternoon, everyone, wherever you are. I'm going to present a few slides on integral benchmark evaluations. Every year, we award one or two new high-quality benchmarks, and so I will give you a little background on what the programs are, the criticality safety and the reactive physics programs, and then also give you an idea of what kind of benchmarks we are looking for, what our priorities are. So benchmarks are really important tools for validation of computational models. And in 1992, the U.S. decided, Department of Energy, that we should take a systematic approach to benchmarking, the evaluation, and the documentation of benchmarks. And so they initiated this program that was managed through the Idaho National Laboratory. And it was just a domestic program at that time. It was known, only U.S. criticality safety experts were involved in it. But later, in 1994, other countries showed interest, and so it became an international activity. And this shows several of the countries that were joining us on that. Here's a nice picture of these various countries. And it was basically governed from that point on by the OECD Nuclear Energy Agency. They managed the program. They renamed it Criticality Safety Benchmark Evaluation Project, and so they did a lot of work. I'll talk about that in a minute. So then, patterned after this approach, the reactive physics community in 1999 did something similar. They initiated a pilot with INL involvement from the beginning, and in 2003 it was endorsed as an official activity of the Nuclear Science Committee of the NEA. It focuses on integral measurements, physics measurements such as buckling, spectral characteristics, reactivity coefficients, and so on. You can read all the effects here. And it involves internationally known reactive physics experts. There's a technical review group that is coordinated through INL National Laboratory. In fact, John Bess, who is on the line, I expect, is the point man for that. Well, the purpose is to collect complete information and on the benchmark experiment. And if you look at the left of the slide, that involves things like the experimental data, the journals, reports, logs, drawings, other environmental variables that are important, anything that really characterizes the experiment very well. Then a computational model is built, and usually we use well-known and accurate computational models like Monte Carlo models, for example, and try to model that experiment. And usually it takes a little work to fill in some of the gaps and find some of the uncertainties and reduce those. But if you can come up with a good match between the experiment and the computational model, then you have an evaluated benchmark, which then has to be reviewed at 3 different levels: internal review, an external review, and then there's a review board at the NEA that has to approve it. If it is approved, then it is published in the handbook, which is on a DVD. You see that on the right. And it becomes available to all the OECD members and they can use it for validating their codes. So where do these handbooks stand at the moment? Well, the criticality safety benchmarks is getting a new edition in September, and it will reflect the contributions from 20 countries. It's got a lot of pages. It's got 568 evaluations of critical, near critical, and subcritical configurations, and other, shielding and so on. And note also, however, that there are 829 unacceptable experiment configurations. Those are configurations that you really couldn't build a good model for. It really wouldn't be a good validation tool. But they're in there and documented anyway, so that nobody else is going to try to make a benchmark out of that same experiment and then fail again. All right, so the reactor physics benchmark handbook actually was issued with the May 2015 edition. Also 20 countries, contributing countries, data from a number of experimental series. You can read this for yourself. And so we have 139 evaluations that are published as approved benchmarks, and 4 are in the hopper. So there's quite a few benchmarks in there. So what have we accomplished with this? All right. So, well, it highlights gaps in the data. In particular, it retrieves a lot of lost data, experiments from expensive facilities that have been, decommissioned, don't exist anymore. We wouldn't, rebuild them because they're so expensive. So very important to retrieve the lost data and make good benchmarks out of those. It helps identify deficiencies and errors in cross-section processing codes and neutronics codes. And it improves the experimental planning, execution, and reporting, because obviously you get a lot of feedback from what works and what doesn't work. So these integral benchmarks should include, they should be based on existing data, and they should include this list here of integral parameters, as many as possible. In many cases, you can't do all of those, but as many as possible we're looking for. And I have made a list here of, let's say, the higher priority type of benchmarks. We're looking for benchmarks on small modular reactors, boiling water reactors, molten salt reactors, nuclear data testing, and research reactors and associated measurements. And there are some examples of each of those. Well, that's really what I wanted to say about benchmarks. So while many reactor measurement and critical experiments may not directly support current mainstream DOE programs, they do serve to fill gaps in nuclear data that may be necessary for future programs. Interested universities may contact John Bess at INL or myself. I'm the federal monitor, but if you want good answers, you better call John Bess, I think. He knows a lot more about it than I do. And that's the end of the presentation. Are there, is a possibility for questions? Yeah. Are there any questions?
First question is, will analytical benchmarks also be considered in this program?
John?
Analytical benchmarks, I think probably need a little more understanding of what they mean by analytical. The key point of the benchmark handbook projects is based on experimental data.
So that's what's said on this slide. Proposed benchmark evaluation should be of existing data. So not just code-to-code comparisons.
How important is it to perform uncertainty quantification? For example, XSEC data uncertainty.
The cross-section uncertainty?
I would assume that's what that abbreviation is.
Okay, I was trying to see if I caught that abbreviation correct. Cross-section uncertainty is important, but it's not part of the actual benchmark analysis. You're looking at, it's kind of a chicken and the egg sort of thing. You need to have existing nuclear data and codes to perform a benchmark evaluation, and yet we turn around and use the benchmark evaluations as integral tests for nuclear data and codes to try to improve them. So typically the cross-section uncertainty analysis is not part of the benchmark evaluation itself. It's something often performed afterwards to show the uncertainty from the cross-section component and compare that with the uncertainties which are due to the experimental measurement, geometries, and material properties of the experiment itself.
But they're often part of the benchmark documentation, are they not, John?
Yeah, often the cross-section analysis sensitivities will be tossed into an appendix. It's actually a growing area that's of interest because we could perform these really good experiments, even modern experiments, and yet our limitations are the nuclear data that define the models that we construct to evaluate them.
Is the review and analysis of an old experiment in shielding considered?
Yes, there's an interest in, especially many of the Sinbad experiments, looking at evaluating those. It would depend on those shielding experiments how they fit into kind of the smaller list that's pulled up right now. If they're like shielding experiments associated with maybe a small modular reactor, a boiling water reactor, kind of that incidence. If it's just a shielding experiment, say you're just doing a rat maze or something and testing particle transport, that is interest for the handbooks, but it's not currently part of the DOE interest.
Are previous treat experiment benchmarks still supported by this call?
In the current call, we are not asking for treat benchmarks. We would like to continue to receive treat benchmarks for the handbook, but we would like to also try funding some additional projects because their funding went for the last NEUP towards treat benchmark work.
Yeah, so the thing I'm worried about is I know that there are some treat benchmarks, particularly dynamic benchmarks that are being, let's say, being selected and being undertaken, and we don't know exactly what they are, but there is a possibility that there would be duplication. So if you want to propose a treat benchmark, which is what we're not particularly asking for here, but we love having them, you know, be sure that you know what's going on out there in the community so that you don't duplicate.
In the second to last slide, are there any priorities compared to other things listed in those examples? Is there some type of a prioritized list, I guess is a better way to put that question.
This one? Well, there was a much longer list, and I asked John to actually reduce it, trim it to something. Since we are going to award one or two projects, it's you know, we'd like to get the higher priority proposals, and this is what we decided is what we're looking for. So you know, you're taking your chances if you do something else and if you propose something else. It's not excluded, but you're taking your chances.
So to clarify, anything on the list is of equal priority.
Yeah. Well, I myself feel that molten salt reactors would be very important because we don't have any benchmarks for those yet, and there's a growing interest in molten salt reactors, both you know, the FHL and the fluid fuel. So those are important, in my opinion. We know that the LWR Proteus experiments in Switzerland, PSI, tend to be very well characterized. And That would be a good one as well. Well, John, you want to add anything to this?
This list, we tried to create something short that indicated where the interests are that were really lacking on the handbooks. There's obviously a lot of experimental data out there that we would really like to have in the handbooks, but we needed a shorter list. These are examples of some experiments that are kind of the quality experiments that could fill those gaps, and we recognize there are other experiments that could equally fill those gaps. There's a lot of need for nuclear data testing and reactor validation. And so we needed something, a shorter list, especially to help the reviewers. That in the previous years we had a couple slides, but we'd end up with responses, all different reactor types, and it made it difficult for reviewers to pick one reactor benchmark concept over another.
Are you interested in specific experiments that could support the validation of high-fidelity NEAMS and Castle neutronics codes?
Absolutely.
Mm-hmm.
Are benchmarks of gas-cooled reactors of interest?
Well, I mean, same answer that I gave before. It's not on the list here. That doesn't mean that it's automatically disqualified. But it's not on the list that we've chosen as our highest priority benchmark. And, you know, part of the reason is that, and John can elaborate on that. You know, how many benchmarks of a certain type of reactor do you already have? You know, you have a lot of PWR benchmarks, and there's a number of gas-cooled reactors. Not so much fast gas, but there's a lot of gas-cooled reactor benchmarks. John, you want to say anything else about that?
Yeah, as you're saying, we do have a selection of various types of reactors in the handbook. You can never have too many, I've decided. Others may disagree. But each experiment was performed for a reason, and even if you have duplicate experiments performed in two different countries, you don't always have the same results. So there's something that can be learned from that. That being said, there are existing gas-cooled reactor benchmarks, mostly graphite. If you're in the thermal, it's like HTTR or VHTRC out of Japan, or HTR10 out of China. Astra out of Russia. So there's a small selection. Currently there is an NEUP that's been awarded in a prior year to University of Florida to work on the gas-cooled fast reactor Proteus experiment. So kind of the shorter list here is to kind of guide things towards where there's data missing in the handbook, where we do not have molten salt reactor benchmarks. We do not have a boiling water reactor benchmark. So things where there's just no existing benchmark data. And so that's kind of where the priority is to start filling in the obvious voids in the handbook, even though there is a plethora of experimental data out there that should and ought to be evaluated for the inclusion in the handbooks.
Yeah, so that's part of the priority selection, but also we are interested in molten salt reactors and in small modular reactors and nuclear data testing. So, you know, that's another reason why they're on this list. They're important to our programs and to our industry, frankly.
What kind of computational tools are required to be used for the benchmark evaluation process? Are there any specific requirements?
John, you take that one, please.
Okay, specifically you want to use tools that will work for what you're evaluating. For example, if you're doing a simple experiment, you look at some of the older benchmarks, they were able to use 1D or 2D codes. But your early benchmarks, you're dealing with simple cylinders and spheres. When you start working on reactor systems, now you're looking at codes with a bit more capability, RZ codes, 3D Monte Carlo codes. Essentially, you want tools that can assess, you can use to actually mock up the model of the experiment and assess the uncertainties. But I wouldn't be using a standard grade school ruler if I was measuring something on the order of micrometers. And so it's the same thing here. Traditionally in the U.S., there's a lot of MCMP or Kino in the Scale software suite. You'll see Tripoli, Apollo Moray out of France. So different countries have kind of their different codes, and so it's kind of up to the evaluator which tools they want to use. If you're looking at using some of the newer tools that DOE's working on, such as like Proteus, you want to definitely, if you use that, you want to show that it applies to what you're looking at. And that's part of the benchmark process. When you mock it up in whatever code you're using to simulate, you show your computational results. And if you're modeling a critical experiment, so K-effective about 1, and your code itself is saying it's 1.7, then it's not very helpful in showing that you can adequately model uncertainties and biases and evaluate the experiment.